So in the last video, we ended by talking about how we can reorder the sequence of producer and consumer writes and reads to memory to get a higher quality loop nest where m is smaller. But we didn't actually get to talk about why m can be smaller. So in the last video, we did mention briefly that when we're doing optimizations of computer programs to try to map them to hardware, it's often more helpful to think about memory as a channel that's used to send information than as a static store of information that is written to and read from. So now that we've reordered our accesses so that we do one write to m, followed by two reads from the same location, we can make m smaller. And the reason for that is easier to see if we trace back the memory dependencies. So if you notice, for example, in memory location 0, memory location 0 is only written by the 0th iteration of the producer loop. And then it's read by, it's read by iterations 0 and 1 of the consumer loop. And then M1 is written by iteration 1, so the second iteration of the producer loop. So the crucial thing to notice is that the last read from M0 happens before the first write to M1. And what that means is that actually all of the use of M0 is done by the time we start using M1. And so actually we could just reuse M0 as M1. We could just say, iteration 1 of the producer loop is just going to write to M0 since we're never going to use M0 again after M1 starts, after the first iteration of the consumer loop starts. And so we can fold up M and reuse it for every single iteration of the producer and consumer loop with only one entry instead of three. So now, the 0th iteration of the producer loop writes to M0, then the 0 and 1th iterations of the, I'm yawning, of the consumer loop reads from M0, and then, cursor's dying on me here. And then the 1th iteration of the producer writes to M0 and destroys whatever value was in there before, and then the 2 and 3 iterations of the consumer loop read that value out, and then we're done using that value, and so the 2th iteration of the producer loop can store to M0 and so on. So we can make m smaller by doing this sort of rescheduling where reads from a memory location are closer to writes. And now actually we can just rewrite this program to say m0 equals in of I divided by 2 plus 2, and then we'll just read out m0 here. So actually we can interpret this loop as the efficient hardware we saw earlier. So we can think of this for loop and if statement as being the controller that is emitting write enables to a register. We can think of M0 as a single location denoted in yellow by this single register. And then we can think of these two operations, the in I divided by 2 plus 2 and out I, as being compute logic, shown in gray and in blue here, that are fed by wires coming in from the outside world and that send data to wires in the outside world. So the outline of the scheduling process that turns loop nests into more efficient hardware is that you want to compute data dependencies, then you want to reorder operations to get reads closer to writes, and then you want to reduce memory sizes and emit a finite state machine and compute logic for your application. So computing data dependencies, it turns out, is kind of a boilerplate task in most polyhedral tools, and a lot of compiler analyses can do it. Usually for the kinds of loops you're sending to hardware, it's not a very difficult task. Then you need to reorder operations to get reads closer to writes, and that's actually where things get very tricky. So if you think about the process of taking just some very general directed graph of nodes and data dependencies and trying to reorder them into a more efficient loop nest, it's a really hard problem. So we can describe these dependencies mathematically in a compressed symbolic form by saying that the ith iteration of the producer sends data to the kth iteration of the consumer whenever k is between 2i and 2i plus 1. So, for example, producer 0 sends data to all values of k such that k is between 0 and 1 inclusive, and notice that producer 0 sends data to consumers 0 and 1. And we'd find something similar for 1 and 2. Producer 1 sends data to 2 and 3, and producer 2 sends data to iterations 4 and 5. And we can describe the schedule of events mathematically in our original program by saying that the schedule for the producer is sp of x equals x, which means the xth iteration of the producer happens at time x. So we do producer iteration 0 at time 0, iteration 1 at time 1, iteration 2 at time 2. And if there are more iterations, we do producer 3 at time 3, but we stop there because there's only 3 iterations. And then the consumer schedule SC of x is x plus 3. So the 0th instance of the consumer happens at time 0, 1, 2, 3. The 1th iteration happens at 1 plus 4 equal to 4. Let's see, 0, 1, 2, 3, 4, and so on. So we start with this mathematical description of the dependencies. And the goal is to create 2 new functions which respect our original dependencies, but that do some computation in a different order, which gets reads closer to writes. So we basically want to create 2 new scheduling functions to map executions that producer and consumer to execution times, that minimize the size of memory. And it turns out that this problem has been studied extensively for decades and decades. There's been a huge amount of effort in compilers and in polyhedral analysis to do rescheduling of loop nests for better memory locality. And the conclusion of 70 years of research has basically been it's just too hard, that in general, this kind of analysis doesn't work very well, and it's still in most real compilers up to a person to get high performance by making decisions about how loops are organized. And the other interesting catch, which I'm going to talk about more in other videos, which comes up a lot when you're doing any kind of automatic restructuring of loop nests, is that even if you could find the perfect mathematical representation of the schedule you wanted, so for example, if you could really find the schedule functions for the producer and consumer that would give you everything you could possibly want, would just be the best possible schedule functions, it turns out that even then you might still be doomed, because it turns out that getting scheduling information from a mathematical function in one of these analysis tools into code in an efficient way is actually extremely difficult, and you can nuke your performance in practice by having really bad code generation. So that's something else to keep in mind. And so what we'd really like is a more limited scheduling model where we can find efficient interleavings of operations. The optimization problem we're solving is tractable, and the schedule is guaranteed to have a form that we can translate into hardware finite state machines efficiently and automatically. And that'll be the topic of later videos in this series. So I'll see you in the next video.